Alright, so we're going to start lesson 6 now, which is on gas law stoichiometry. Basically, we're going to be walking through 2 examples to start, and then I'm going to have you guys try one, see if you can understand how it kind of works and how to figure out how you need to solve to get the correct answer here. So we're going to start with this first example. It says a sample of oxygen gas is a volume of 2.5 liters at STP. I will always tell you what STP means. STP stands for standard temperature and pressure. Standard temperature is 273 Kelvin, whereas standard pressure is 1 atmosphere. We want to know how many grams of O2 are present. So this is where your stoichiometry skills from earlier in the year are going to come back into play here. So as we're thinking about how to solve this problem, we're going to want to think about our stoichiometry skills and those bridges that we worked on earlier in the year. So if we start thinking about where to even begin, this is going to originally read like a gas law problem that we've been solving. So the first thing we need to do is we need to start identifying all of the different variables that we have. So you'll see in this problem you were flat out told this volume here, and then this STP gives you both the temperature and the pressure. So I'm going to start charting like we've been doing before. So we have a volume of 2.50 liters, okay? Then we have our standard temperature. So our temperature is 273 Kelvin. Our pressure here is 1 atmosphere. Then at this point, you're going to want to kind of look at what we need to have. So we need grams of O2. Now, if we start looking at what we have so far, we've got 1 volume, 1 temperature, 1 pressure. So if you look through your list of gas laws, the only one that really makes sense to choose now is PV equals nRT. So I'll write that down here. Then the only thing that we have left to solve for is this N here. So we ultimately need to solve for N first, and then convert that from moles, which is what it's normally in, into grams. Now, we have that R value is that constant, so I'm just going to write that down. Alright, so now we have V, T, P, R, and we're going to solve for N here. So I'm first going to rearrange this to solve for N. To do that, I'm going to divide both sides by RT. So we have N equals PV divided by RT. So then I'm going to start plugging in some numbers. So my pressure is 1 atmosphere. My temperature is 273 Kelvin. Sorry, I should have the volume up top here instead. It should be 2.50 liters. Then R goes down here. Liters, atmospheres, mole, Kelvin. Then here's our temperature, which is 273 Kelvin. Okay? So again, this unit here for R is going to have our units cancel, so liters cancels, atmospheres cancels, Kelvin cancels, we'll be left with moles, which is what we want. So when you go ahead and type this into your calculator, making sure you're putting parentheses in for the bottom here, you're going to get that we have 0.112 moles of O2. So 0.112. Okay, that's the answer we're looking at here. Now, we have to convert it one step further since the question's asking us for grams of O2. Right now we have moles. We got to get to grams. That was one of those conversions we were doing a lot in the stoichiometry unit. We were talking about how in the world you're going to convert one to the other. So we're going to first write that down in the top of a bridge here. So I'm going to write it down here. Bridge is coming back into play. So we've got this value here, 0.112 moles of O2. Remember that whatever unit you see up here has to come down here as well. So we have moles of O2. Then we're trying to get to grams, so I'm going to put grams of O2 up top here. To figure out this conversion here from grams to moles, we're going to use the molar mass. If you remember doing this from earlier in the year. So if you look up at the periodic table, oxygen has a molar mass of 16 grams per mole. Remember we have O2, so we have to double that. So that's going to become 32. Once again, each oxygen is 16. O2 means we have 2 of them, so 2 times 16 gives us 32. That's the number of grams in 1 mole. Okay? So we're going to go ahead and calculate that out. If you take the 0.112 times 32, you're going to get 3.57 grams of O2. And this is going to be our final answer here. So, first part shouldn't be too bad. That's what we've been doing gas laws. The only new step here is the stoichiometry part, where we're going to go from moles to grams. And then if you go ahead and calculate that out, multiply the top, divide by the bottom, you get 3.57 grams, which should be your final answer there. Alright, so let's go ahead and move on and do something that looks a little different here. So if we look at this second example, this one says, what is the molar mass of a gas that has a density of 0.0045 grams per liters at 25 degrees Celsius and a pressure of 1.12 atmospheres? Now, this is a new equation that I'm introducing to you guys here. We have molar mass is equal to D, which is density, R is that same constant that we have for ideal gas law, T is temperature, P is pressure. This is basically a rewritten form for the ideal gas law whenever you have density involved. So notice this right here is just your unit analysis, which means that I'm showing you the units for each of those. So density should be in grams per liters. This is the unit for R, all four of these. Temperatures in Kelvin, pressures in atmospheres. So when you do a read through your question, you have to make sure those match. So grams per liters looks good for density up here. This is obviously the constant. This is in Celsius, so we need to convert to Kelvin, and atmospheres looks okay for our pressure. Okay? So we're going to kind of treat this to begin with how we normally have been treating the problems, starting to list out the variables, only we're going to use this new version of the ideal gas law here when we have density involved. So just kind of writing out what we have again, the first thing I see there, I see a density, so I'm going to write that down. So D is 0.0045 grams per liter. Then we've got our temperature is 25 degrees Celsius. Converting that to Kelvin, we add 273 to that. So that's going to take us to 298 Kelvin. R is the same constant. I'm just going to rewrite that. All four of those units there. And our pressure we have is 1.12 atmosphere. Okay, so I have everything listed here. If I look at that equation there, the molar mass is what it's already arranged for. I'm going to abbreviate molar mass as MM just to save some time here. So my molar mass is equal to my density times R times T divided by P. At this point, everything's converted how I need it to, so I'm just going to start plugging in some numbers here. Okay, so on the top here I have the 298 Kelvin at the end, divided by the 1.12 atmospheres. So on the top, density is a 0.0045. Then we've got the 0.08206, which is that constant. At the end here we have 298 Kelvin, divided by the 1.12 atmospheres. So if you go ahead and plug that into your calculator here, multiply across the top, divide by what's on the bottom, you should get as your molar mass that we have 0.0983 grams per mole. Okay, so this right here, this gas and this answer that you're going to get for this molar mass here, obviously is pretty darn low. It's not super realistic in terms of looking at the periodic table and trying to figure out what that gas is, but this is just an example problem using the numbers, seeing if you can use this molar mass. Okay, so that's it for first two example problems. The next thing I'm going to have you guys do is to try one on your own, see if you can figure that one out.